the DSC. We also looked at a failure of PVC. In this case, we're actually using the DSC to confirm or not confirm that our sample is what we think it is. This was presented to us as being PVC, and that's the green sample at the top. We ran two different reference samples of PVC from our lab, a blue one, which was a flexible PVC, so it's plasticized. The red curve is rigid PVC. And we see that these curves look nothing like our sample. PVC typically is not crystalline. It has just a TG. So this is information that tells us that perhaps this isn't really PVC, or that there's something else there as well. So you can see how we can use it to confirm composition in some cases. I mentioned oxidative induction time, and the curves that we see here are related to that measurement. Basically, under actual use conditions, polymers will often experience degradation from oxidation. And oftentimes manufacturers add antioxidants in order to slow down that process. And we can use DSC to measure how well those materials are working. So take our sample and put it into an open pan. Doesn't have a lid on it in this case. We're going to heat it up to a specific temperature, usually 200 C for olefins in nitrogen. And then we're going to switch to oxygen and see how long it takes for the degradation to occur. And in this case, the green curves represent the heat flow of the sample, and you can see that at some point you start to see an exothermic change, and that's where the degradation is occurring. The time from where you did your gas switch until that onset is our OIT, or oxidative induction time. The sample on the left has a much lower OIT than that on the right. This may mean that either there's less antioxidant present there, or that there's a less effective antioxidant in that sample. So this would be a quick way to measure efficacy of those kind of materials. I will point out that there's an ASTM standard for this, and that's B3895 in case you're interested in more information. Now, I mentioned modulated DSC. This is a newer technique, but it does have a lot of power. It can be used to separate out overlapping transitions. Now, the conventional DSC, as I mentioned, usually have a linear heating ramp with 10 C a minute or so. With modulated, you actually overlay that with a sinusoidal oscillation of temperature, and that allows you to separate your signals into reversing and non-reversing heat flows. So the green curve here is the total heat flow, and that's equivalent to what you would see with conventional DSC. The blue curve is the reversing heat flow, and it shows heat capacity related events like TG or melting. The brown curve is non-reversing, and it shows kinetic related events like crystallization. So we see here that in our green curve, we have a nice melting point at around 220, 230, as we'd expect with this sample. But we find that in our brown curve, we actually have an exotherm occurring. So what we're seeing here is that we have simultaneous crystallization and melting, but this is something that we would never know unless we ran this particular modulated test. So it can give you a little bit more information about what may be really going on with your sample in some cases. Now, to switch gears a little bit, I'm going to talk a little bit about thermogravimetric analysis. DSC is usually used to look at the temperatures where polymers are processed or used. TGA usually encompasses a much broader temperature range. We usually have, again, a small sample, about 10 milligrams, and we're heating in various atmospheres, air, nitrogen, or other gases in some cases. We can see here the TGA pan is on the hang-down wire. The black cylindrical piece is at the furnace, and that would raise up and control the atmosphere or our sample. So how it works, we have our sample in a platinum pan, and we're heating at some rate, or we're sitting in a specific temperature for a certain amount of time. And during that test, the mass of the sample is continuously measured by microbalance. We can run in air, oxygen, nitrogen, or we can actually switch gases during the run depending on what the goal of the study is. So by measuring the mass during the test, we can actually see at what temperature that sample starts to lose mass or volatilize. So what does it tell us? Well, the most obvious thing is thermal stability, because of course that's related to the mass loss. But we can also get an idea of compositional analysis on filler content. We use this instrument in some cases to prep samples for other techniques. Using different heating rates, we can get an idea of the kinetics of degradation of samples. And out of the VFC that we discussed, the results can often be heating rate dependent. So that's, again, something to be aware of. So here we see an example of thermal stability. We have weight percent on the y-axis and temperature on the x. These were samples that were run in our lab all under the same conditions, 10 C a minute under nitrogen. They have very different degradation profiles. You can see that PVC starts to degrade or lose weight at around 200 or so, versus up in the 500 degree range for polycarbonate and TPS. And acrylic and HDPE is somewhere intermediate there. So this is a good technique to determine how your sample is going to behave under certain thermal conditions. Now we can also use TGA to look at filler level in samples. Polymers are often filled with inorganics, talc, titanium dioxide for various reasons. The polymer portion of the sample is usually going to burn away by 400 to 500 C, especially if you're in air. And the mass remaining at the end of the run then is going to be representative of your filler. So this is a way to measure how much filler is in your sample. In this case, we were doing some in vitro aging of a sample that was filled. And we see that the green curve is the time 0. The blue curve is after 8 days, and the red curve is after 16 days. And we see that our filler level appears to be increasing. Obviously, we're not creating filler during our in vitro aging, but we are losing polymer, and this is one way that we can measure that. Now, we could also then use this as a sample preparation technique, because we could then take that filler that's left in the pan and subject it to another test, something like scanning electron microscopy with energy dispersive X-ray analysis, or SEM-EDS, and that allows us to then measure what elements might be present there. We can also measure carbon black using this technique, and that's what we've done here for a tire sample. Carbon black will not burn away even up at 900 C if you're in nitrogen, but it will burn away in air. So we can exploit that and do a gas switch in the middle of our run, and that's what we see here, where our curve seems to be going backwards in temperature. That's part of the test. And we can then get an idea of not just the inorganic filler, but also how much carbon black is there. And the details of this are outlined in ASTM D6370. So I want to touch briefly on a couple of other techniques. One of those is thermomechanical analysis, or TMA. You see an instrument for that here. Sample size, again, is fairly small, maybe a 1/4 inch diameter and probably between 2 and 10 millimeters thick. And this technique works by having a quartz probe apply a constant force to your sample. Usually it's in the range of millinewtons, so it's a very small force. And that probe is attached to an LVDT that constantly monitors its position in the y direction. So during the test, if your sample is changing in dimensions, that probe may move up and down, and therefore the instrument's going to monitor that, and that gives us information about the sample. We can do this over a temperature range or isothermally, and it's also possible to run in various atmospheres as well if that's of interest. So what does it tell us? The most obvious application is coefficient of thermal expansion, or CTE. This is one way to measure that. We can also determine softening point, glass transition. We can monitor curing and crystallization, because those are both techniques that often lead to shrinkage of our sample, so we may see a difference in the probe height because of that. And as with the other techniques we've mentioned, again, the results can be heating rate dependent. So here's a typical TMA scan where we have probe position on the y-axis and temperature on the x. We see just a linear response in this case, but the slope of that line is proportional to the coefficient of thermal expansion, which in this case is about 214 per degree C. Another common technique in the labs is melt flow index, or MFI. This is a fairly crude method, but it is quick and easy and useful for some quality control applications. It's a simple test where we place pellets or powder into a heated barrel. We put a specific weight on top, and we measure how long it takes for a certain mass of material to flow through a die. The results are reported in grams per 10 minutes. It's roughly related to molecular weight and viscosity, but it is a single point measurement, so it can be misleading at times. But it is good to determine lot-to-lot variations and that sort of thing, and it can be used in line with processing. So in that case, it can be quite popular. There's an ASTM standard against D1238, and this is something that you might commonly see on spec sheets or technical data sheets. The last technique I want to discuss is dynamic mechanical analysis, or DMA. This is a very complicated area and could easily take several talks, but I just want to very briefly scratch the surface here and let you know maybe what its usefulness might be for you. It's used for solid samples, and you can see our instrument here. The little white rectangle gripped by the metal pieces is the sample in this case. So it works by applying some sort of oscillatory deformation on the solid sample. We have many modes of use for this. We can do films in tension. Stiffer samples can be run in torsion. There are single and dual cantilever modes, bending modes. Some instruments have shear modes, and the list can go on and on. It allows you to measure modulus of your sample. And again, you can do isotherms, you can do temperature profiles, much like the other techniques that we've talked about. What does it tell us? Well, it's one way to get TG. It's especially good if you have a very crystalline or cross-linked sample. You can imagine that if you have a lot of crystallization or cross-linking, the amorphous fraction would be low, and therefore the TG signal that you would get from that if you try to run DFC might be too low to see. DMA, though, is very, very sensitive to this, and it would be the preferred method to measure TG in this situation. We can also use it to measure modulus. If we do a variety of temperatures and frequencies, we can then use time temperature superposition, or TTSP, to actually predict how our sample might behave at either very long or very short times that we can't really experimentally access. We can run creep experiments with DMA. We can measure curing behavior of materials. And in some cases, for very thin films and fibers, DMA can actually be used to do stress strain measurements of failure, much as you would on a test frame. But again, results are heating rate dependent, so that's kind of the recurring theme here. You want to be careful when you're comparing results from different sources. So this is a typical DMA graph where on the left-hand y-axis we have storage and loss modulus. The right-hand y-axis is tan delta. You can see in the red curve you see a drop in modulus, and as we mentioned before, that's usually related to TG. We also see a peak in the blue curve, or tan delta. Again, that's very indicative of TG, and we can use that peak to determine what the glass transition temperature is for this particular material. I want to go over just a couple case studies here. The first was a broken conveyor belt. We had a customer come to us with the situation where a conveyor belt that was being used in a particular application was failing, and it's too short of a time frame. So we see here on the left is a new part, and on the right was one of the used parts that had failed. You can see the used part looks sort of scratched and certainly discolored, and obviously it's also broken, which is a major problem. So we wanted to do some comparative analysis to see what might be causing this degradation. So here we see DFC of these two samples, the new belts in the green on top and the used belts blue on the bottom. What we see right off is that there's a difference in the areas of the melting peaks, which means there's a difference in crystallinity. We also see that the broken part has maybe a slightly lower melting point, 173 versus 175. This difference isn't conclusive because that's pretty much within the uncertainty of the measurement, but that combined with the difference in the crystallinity implies that there